Okay, hi everyone. Welcome to another episode of Science and Technology Q&A for kids and others. I think it must be a sign of the recent Earth Day that there are questions here about climate change and so on. If there's a way to create climate change, that must mean there's a way to reverse it. We comment on that. Well, let's see. Okay, let's talk about global climate and those kinds of things. So it's a complicated subject because it's a mixture of science, public policy, ideology, politics, lots of other kinds of things. I can talk mostly about the science side of it. The question is, first thing to say is the climate of the Earth has changed over the course of the time that the Earth has been around. It's changed pretty dramatically. The oceans have gone up, they've gone down, the average air temperature has gone up, it's gone down, the carbon dioxide concentration in the atmosphere has gone up, it's gone down. Things were very different at different times in history. And if you look at charts of many kinds of parameters about the atmosphere, they sort of bounce around kind of randomly. There are a few, like that it looks like we humans have actually had an effect on. But there are many others that we haven't had an effect on, or at least not one that is easy to detect. And the thing perhaps worth understanding is, well, is the question of, so what if you have an effect on some parameter of the Earth's atmosphere? What consequence will that have? And that's where things get quite complicated. And it gets complicated to see so let me tell you a little bit of the history as far as I know it. When I was very young, I think one of my earlier science memories from when I was like 2 or 3 years old. I lived in England. There was an extremely cold winter, 1962 to 1963. And the word was, there's going to be another ice age. So that was ice ages are something that happened in the history of the Earth every so often, and it's not a regular kind of thing, although there's some evidence of some kind of regularity in that pattern. The Earth gets very cold, and the area of the Earth that's frozen right now, the Arctic, expands to be a larger part of the Earth. And then the ice age is over, and all the glaciers melt and withdraw, and so on. Much of the topography of the hills and valleys and so on in lots of places is a consequence of where glaciers were in the last ice age. So I'm trying to remember how long it's been, maybe 10,000 years, 20,000 years since the last ice age. Maybe I'm wrong a little bit by that. Maybe it's as long as 50,000 years, I'm not sure. But a lot of features of terrain were formed by those glaciers in the last ice age. And so there are all kinds of funky things, like there's an island off the coast of Massachusetts called Nantucket that has this funny horseshoe shape. And you wonder how on earth was an island made in that shape? And the answer is there was a glacier that was pushing down through other parts of Massachusetts, and it pushed a bunch of mud and gunk ahead of the glacier. And it's called, in geology, it's called the terminal moraine, is what gets left over when the glacier has pushed that far. And this is the stuff that got pushed ahead of the glacier, and it leaves this kind of horseshoe-shaped island. And so there are lots of features of current topography that come from the last ice age. And there are different, there are parts of the world where there was things what are now islands were not islands, and so on and so on and so on. Things have changed. Things will go on changing. That's the nature of geology and so on, and the nature of planetary science, that there is progressive change in the climate of planets like the Earth. Now, what are the consequences of those changes? Well, for example, I think it was around 1650, there's a thing called the Maunder minimum, which was happened to be correlated with the disappearance of sunspots on the sun, and it's not clear how significant that was. But in any case, it was really cold, like in Europe. And for example, in various rivers in Europe, they never melted during the year. They were frozen the whole year. And this happened for, I don't know, 50 years or something. And then things started to warm up again. And so there are these variations in average temperature that happen in sufficiently short timescales that it's within recorded history. These are not kind of geological. It's not like the dinosaurs had it one way and we have it another way. It's in 1650, it was something different, and now it's changed. And so there are these progressive variations of things like temperature. But back to the story of at least my experience with these kinds of things. So 1962 to 3, people said, there's another ice age coming, terrible. Everything's going to get very cold. Okay, so, well, that didn't really pan out. And the reasons for expecting that were a bit unconvincing in the end. I'm not sure that I know all the reasons that were given at the time, but it didn't pan out. It had to do with things about the Earth's orbit. It had to do with some other kinds of things about the sun and so on. Didn't turn out to be correct. Okay, the next important thing that happened from my knowledge of this history is a quite different episode, which was the episode of the ozone hole. So in the Earth's atmosphere, there's light that comes from the sun. Most of the light from the sun makes it to the Earth's surface. But in addition to visible light coming from the sun, there's also ultraviolet light. That is higher frequency electromagnetic radiation, higher frequency photons come from the sun. And that ultraviolet light would be pretty bad for us. I mean, it's the ultraviolet light is the main thing that causes us to get get sunburn and things like this. It's also bad for our eyes and so on. Ultraviolet light is not very good for us. A certain amount of it gets through the Earth's atmosphere, but a large part of the ultraviolet light from the sun is blocked by this ozone layer in the upper atmosphere of the Earth, which conveniently is there. So that means that we biological organisms didn't have to evolve to fend off the ultraviolet radiation. It was blocked for us by the Earth's atmosphere. So ozone, just to explain what that is, so the Earth's atmosphere is about 78% nitrogen, 20% oxygen. Most of that oxygen is in the form of O2. That means a molecule in which there are two oxygen atoms bound together. But there's a sort of slightly less stable form of oxygen, which is O3, 3 oxygen atoms bound together in a molecule. That's ozone. Ozone is a good absorber of ultraviolet radiation. And ordinary oxygen molecules can be turned into ozone by the effects of ultraviolet light in the upper atmosphere. And so in the upper atmosphere, there's a whole bunch of ozone. And that ozone blocks the ultraviolet radiation and means that we don't get sunburned, and it's all a good thing. Okay, so then there were some things called CFCs, fluorocarbons, I guess. They're molecules. They are molecules that involve fluorine and carbon and hydrogen and so on. And those particular substances, the gases, were used as propellants in aerosol cans. So when you have one of these aerosol cans and you press the button and it squirts something out at high speed, that was, whether it's whipped cream or something else, the CFCs were used as the gas that was used to sort of push things out quickly in an aerosol. Okay, well, it turns out CFCs interact badly with ozone, and they basically destroy ozone. And so everybody was up, sort of we're making our, whatever it is with our aerosols, our aerosol cans, and they're powered by the things that are pushed out with CFCs. And the result of that is lots of CFCs in the Earth's atmosphere, and that interacted badly with ozone and started destroying the ozone in the upper atmosphere of the Earth. And in particular, there was this apparent hole in the ozone layer that developed initially over the Antarctic. And people were very worried that, it's going to destroy all the ozone in the atmosphere, and we're all going to get sunburnt, and it's bad news. Okay, so then the various governments got together and sort of banned CFCs. So can't use them for aerosols, and aerosols started to be done a different way. Okay, the good news was that fixed the ozone hole problem. So in other words, people learnt that that was kind of a good experience of, well, we goofed slightly. Nobody figured out that CFCs used for aerosol cans would produce this bad effect on the ozone layer. Turned out it happened. We rolled back using CFCs. The ozone layer went back to normal. We don't get sunburned any more than we would normally. It's all good. Okay, so that was sort of that episode. Well, then another thing that happened was during the Cold War, the time when the Soviet Union and the US were kind of in this standoff, starting in the 1950s, 1960s, 1970s, most of the 1980s. The sort of the big threat was, the thousands of nuclear missiles that both countries had. Would something happen and they'd all, they get released and there'd be some giant nuclear war. One of the things that was thought to be a disaster from that nuclear war was this thing called nuclear winter. And so the concept was you release you detonate a bunch of nuclear weapons, and you end up throwing dust up into the upper atmosphere, and that dust would block the sun and would cool the surface of the Earth, and you'd have kind of this artificial winter. Now, perhaps something to be worried about, because probably it happened to the dinosaurs. Probably when the asteroid hit the Earth 65 million years ago, one of the things that it did was to throw dust up into the upper atmosphere that blocked the sun for a year or two. And if you're a reptile, a cold-blooded reptile, and things get really cold, it's sort of bad news. And that might have been one of the things that was really bad news that caused the extinction of the dinosaurs. In the 1800s, there was a volcano called Krakatoa in Indonesia that was a giant volcanic explosion. And it too put a bunch of dust into the upper atmosphere of the Earth, and it cooled the Earth a bit for a year or two. So there's sort of evidence that could have happened. So this was kind of one of the really, really bad things about having a nuclear war. Well, there are lots of bad things about having a nuclear war, but one of the really bad things is it would lead to this nuclear winter, and it would make the Earth cold for some number of years, et cetera, et cetera, et cetera. And there was evidence from planetary exploration on Mars, for example. There was evidence of dust storms that might have had, global effects for some period of time, and so on. And that was sort of used as a piece of that story. A popularizer of science, Carl Sagan, also scientist Carl Sagan, was very involved in the whole nuclear winter story, which became sort of a mixture of a science story and a politics story. That's one good reason not to have a nuclear war. I think there are others as well. But okay, so then we come to more modern times, and people were trying to figure out the climate of the Earth. What would be the evolution of climate on the Earth? People have been trying to do weather forecasting back in the 1950s. So how did weather forecasting get done originally? So what do you need to forecast the weather? There's a pattern of airflow around the Earth. There are high pressure areas where the pressure of the Earth's atmosphere is higher. There are low pressure areas. There are fronts between the high pressure areas and the low pressure areas. There are places where there's cloud cover. There's places where there's moist air and so on. There's different humidities, all these kinds of things. So back up in the 1930s, 40s, and so on, there was some, and earlier, there were efforts to do weather forecasting by just making measurements and weather stations around the world, and just sort of knowing, if we have a high pressure area, it will push itself out in this direction, and the front will move in this direction, and the wind is going this way, and so this thing will move. And it's something that was done by human meteorologists, human weather forecasting people. Actually, the thing that really launched that was the availability of weather stations, getting weather data around the world. And there was a chap called Fitzroy, who actually was the captain of the original Beagle ship that took Charles Darwin around the world as a naturalist, where he collected all these specimens that led him to formulate this idea of natural selection and so on. Anyway, Admiral Fitzroy was, among his other achievements, later in his life, after the voyage of the Beagle and so on, he started, for the British Admiralty, the British Navy, he started this big network of weather measurements around the world. to try to start doing weather forecasting. So sort of the raw material for weather forecasting was initially, and is today, weather stations. And today there are around 30,000 professional weather stations around the world, and lots more not so professional weather stations that feed data into a big network that is sort of aggregated by the World Meteorological Organization, but and aggregated in the US by NOAA and so on and so on and so on, and the National Weather Service and such like. But okay, so for a long time, the way weather forecasting was done was with these rules of thumb about, oh, there's a high pressure area here and it moves this way and as a result of winds and et cetera, et cetera, et cetera. Okay, in 1950, actually particularly as a result of a mathematician named John von Neumann, had this idea, we're going to be able to use computers, these new computer things. They're going to make it easy to do weather forecasting. We don't have to have humans doing weather forecasting anymore. We'll just automate it with computers. Okay, turned out to be easier said than done, because it turns out that the mathematical equations of fluid flow are very difficult equations to solve, even for a computer. And they're difficult both in their structure, and they're difficult because they depend sensitively on the particular values of temperatures in one particular place. Can have a big effect in some situations on the predicted weather some number of days in the future. But through the 1960s, there progressively developed more computerized weather prediction. And there are these centers for weather prediction. There's one in Boulder, Colorado, in the US. There's one in Reading in the UK, I think, for part of Europe, although I don't know what's happened now that the UK has exited with Brexit. I don't know what's happened to the European weather prediction operation. Probably, well, I don't know what's happened to it. But in any case, what these are big computer codes being run, taking as input data from the weather stations around the world. So weather stations will measure every 15 minutes or sometimes every 5 minutes. They'll measure temperature, wind speed, wind direction, humidity, and so on. Very often, well, basically every airport has a weather station associated, weather measurement thing associated with it, because it's used to provide weather information for planes that are coming into that airport. But there are, in addition, other weather stations that exist in different places that all feed their data into these various networks. And so that's the input. The weather stations give the input. Then there are these big computer codes that run. And there's sort of been a big effort spent to figure out to be able to do more weather prediction. And so the shorter the time you're trying to predict for, the easier it is to predict. And so if you're predicting for a day, it's fairly straightforward. If you're predicting for 3 days, it's quite kind of more difficult. 5 days, even more difficult. By the time you're out at the stage of months and things, it gets to be really, really difficult. And you get to be wrong a lot of the time. It's also the case that there are different parts of the world where it's easier and more difficult to predict the weather. So there are places inland where essentially there'll be some pattern of air and clouds and so on. It's just being blown by the wind without much change across this area of flat plain. And so there it's quite easy to do the prediction. In other places, like when I was growing up in England, England is an island with, ocean around it and all kinds of the Gulf Stream current coming from the Gulf of Mexico and so on, and just a lot of complicated stuff. Weather forecasting is pretty hard for the UK. And so the weather forecasts didn't tend to be terribly accurate. But over time, computerized weather forecasts have gotten more accurate. It's still very difficult to do weather forecasting, and things like clouds are really difficult to deal with, the effect of clouds and the details of the structure of clouds and so on. And there's still, I don't know how many layers of the atmosphere are now accounted for, but it may be tens of layers at most, which doesn't really account for all the details. Because, for example, the surface, the wind at the surface of the Earth, but the wind can be way different. You can easily have, at the altitude that planes fly at, you could easily have 100 mile an hour, 200 mile an hour winds, which you don't normally have anything like that at the surface, because at the surface there's sort of a friction from the air blowing across the solid ground that slows the air down. That doesn't happen as you get higher up. But there are many details of that are hard to know. So in any case, There is this effort in weather forecasting, weather prediction. It's gotten progressively better. There are kind of modern innovations that one can try and use with machine learning and so on. We've done all kinds of experiments using machine learning to do various kinds of weather forecasting. You can do a certain amount by looking at weather radar, where you're seeing weather radar is something where you can see rain and so on from because the raindrops reflect back the radio waves that are part of the radar, and so you can detect where the rain is. And by using that, you can get some more information for weather forecasting. But so short-term weather forecasting, few days, something we've kind of learned how to do. We've got computer programs that do it. It's been a big struggle, but it's sort of more or less there. Okay, now the question is, what's going to happen to the global climate of the Earth a year from now, 2 years from now, 5 years from now? That's really hard to figure out. And it's hard both in the mathematical computation that has to be done and in the question of are the models correct? Clouds have been a very big deal in those kinds of models. They're still dealing with only just a few layers, I don't know, maybe 5 layers or something of the Earth's atmosphere. And it's really difficult to do those computations. And so that's, when people say, what's going to happen to the Earth's climate? What's going to happen if this or that happens? Well, you have to run this model. And these models are really hard. And it's really hard to know if you're getting the right answer. And sometimes people say, well, let's run a bunch of different models and see whether they all give the same answer. Well, sometimes that's a good idea, sometimes it isn't. I'll tell you something about weather forecasting. So sometimes it'll say, X% chance of rain. Some forecast will say there's a 30% chance of rain. What does that mean? Because you've got a weather model that, given the temperatures and weather and wind speeds and all that kind of thing of the measured at the weather stations, you just compute what the predicted outcome based on this weather model will be. It just gives you a definite result. Okay, so what's actually happening is, because you haven't measured every temperature and every wind speed everywhere, there's pieces you don't know. And so what people do is they say, let's run the model many times. Let's run the model first. We know what it is at the 30,000 weather station positions, but we don't know what the values of the temperature and wind speed and so on are at other places. So let's fill those in kind of at random. And let's do that, let's say, a dozen different times. We'll fill in different sort of random values in other places. And let's do these calculations for a dozen different possible initial conditions, for a dozen different possible sort of choices of the current temperatures on the Earth and so on. And let's see what results we get. And so the answer will be some of those, with some of those assumptions about information you didn't know right now, it will rain in wherever. And with some of those assumptions, it won't rain. And so when people say there's a 30% chance of rain, roughly what that tends to mean is 30% of the models that will run say there's going to be rain, and 70% say there isn't going to be rain. Now, I mean, it's a tricky business because sometimes there's a question of you can't run it for all possible things you don't know about. And there's a question of how clustered are the results. And sometimes there are different kinds of weightings. And sometimes even with a single, the main weather models that get run in the US are run by the National Weather Service. Well, actually, I think they're run by NOAA and distributed by the National Weather Service. But you can end up with different weather outlets telling you different things about what the probability of rain is. And sometimes that comes because they looked at these collection of different forecasts from different runnings of the model, and they had different ways to weight those different pieces of the forecast, and so they end up with a different percentage. Okay, so anyway, that's the story for kind of weather forecasting. But again, then the question is, what happens when we try and project far into the future? We try and work out, 50 years from now, what's going to happen to the climate on the Earth? It's just really, really, really hard. And there are some large-scale phenomena that are known, like the El Nino phenomenon, which is a sort of ocean current air thing, which is a kind of a season-long kind of phenomenon. And there are other things that are slightly larger scale. I mean, when you have a hurricane, it comes through, but it all happens in a week or two. It's all done. There are some slightly longer term structures that develop in the Earth's atmosphere that allow you to understand things. Then there are things that have longer sort of time horizons, like the melting of glaciers, the sea ice disappearing and reappearing and so on. Those have slightly longer cycles. Okay, so then the next question is, so okay, next thing to ask is, so it's very hard to do these predictions. So the next question is, what's actually happening? What's actually happening on the Earth? And as I say, in the history of the Earth, the climate has changed, things have happened, but let's see what's been happening more recently. Well, first thing to ask is, what data can we get from the past? I believe the longest time series of temperature measurements on the Earth, I think, is the Central England temperature series, which I think goes back to the 1600s. Somebody's been measuring, different person presumably, has been measuring the temperature in somewhere in England for that period of time. Most of the time series of temperature measurements go back to the about a century or so. Some of them a little bit less than that. And so you have all these data points and there were a lot of different measurements made, a lot of things that make it really difficult to understand things from those 30,000 time series of data. There's about 5 terabytes of data that exists in the sort of standard collection of data about weather, climate in the history of the Earth from ordinary weather observations. And so one thing, I remember looking at this years ago, is like, what can you see about the trends in, for example, the average temperature of the Earth from those measurements? Well, it's really difficult because those measurements have been made at very populated places. There are very few measurements in some parts of the world. The places that have lots of airports, lots of fancy buildings and so on, have much higher concentration of temperature measurements than other places. And then the other problem is, used to be the case in the US, for example, that there were often temperature measurements made at post offices. And those post offices for a while were out in the middle of nowhere and out in the countryside. But eventually the towns grew up and you end up with a post office in the middle of a town. And one feature is as soon as you have things like asphalt on the ground that's sort of blackish, it absorbs sunlight, it gets warmer than something which is just a field of grass or something. So things, if you are looking over timescales of decades, the things can change just because the temperature measuring device is in a different environment than it was in the past. So it's pretty difficult to take that data on its own and figure out much at all. For a while, people were saying, oh, there's evidence the Earth is warming. Sometimes they said it was cooling, but usually they said it was warming. Based on that data, I was never able to pull out any reasonable signal from that data alone. There's other kinds of data. There's data from ice cores, of drilling down in the Antarctic or something and seeing the different amounts of pollen and other kinds of things that you get in different levels in the ice as a reflection of the average temperature of the Earth. There are also tree rings where when there's trees grow every year, they because they grow differently in different seasons of the year. If you look at the slice through the tree, you'll see that there's thicker, there's darker areas and lighter areas that go year by year. And if it was a better year for the tree might have grown more that year, and so the tree ring will be thicker. And so there's some data from tree rings and so on about climate going back for the time that trees have been, the particular trees that you can that are around today have been around. So maybe most hundreds of years, maybe 1,000 years, something like that. So there's some data from these kinds of things. A bit controversial, some of that data. There's also the one thing that's actually easier to measure is carbon dioxide levels in the atmosphere. And that, although its effect is less obvious, but the amount of carbon dioxide in the atmosphere is determined by, well, how much you put there. And what puts carbon dioxide in the atmosphere? When we we breathe in oxygen and we breathe out carbon dioxide. Plants work the opposite way. They pull in carbon dioxide and they produce oxygen. Burning things typically pulls in oxygen and releases carbon dioxide. So when we are off burning things like we have, internal combustion engines in cars and they're burning gasoline, or we have coal fuel plants and they're burning coal, or we have airplanes and they're burning airplane fuel, these kinds of things. Those kinds of processes of burning things produce carbon dioxide and bring in oxygen. So it's been possible to measure with satellites, well, it's possible to measure quite directly the carbon dioxide levels in the Earth's atmosphere. And yes, they have been going up. So regardless of what happens with the temperature, which is a little bit harder to figure out, there's some data from satellites on sort of average temperatures, which also I think shows a systematic increase. And that's not based on just individual measurements at weather stations and so on. But the basic answer is, well, yes, there has been over the course of the last 100 years or something, an increase in carbon dioxide levels, maybe an increase in average temperature, etc. And that is presumably caused by us humans. Now, meanwhile, there's just variations going on in average temperatures and sea levels and things like that that happen just as a result of change of climate, that happen for reasons that we don't understand very well, to do with the way the sun is working, the way the Earth's orbit works, the way the atmosphere works, et cetera, et cetera, et cetera. There are complicated cycles not very well understood. But yes, we have some effect. There's 7 billion of us, and it's sort of not totally surprising that we have some effect on the Earth. In a sense, it's impressive that we can have an effect. We might have thought, that all the things we do, the Earth is just going to keep going and nothing much is going to happen. But we have some effect. So now the question is, what are the consequences of that effect? So the next question is, what happens if you have a lot of carbon dioxide in the Earth's atmosphere? Parmenides just commented here on one point here. Venus is a bad case analysis for what happens if you just have. I think it has a lot of carbon dioxide. It has some other gases as well in its atmosphere, but basically you can end up with a situation where, because there's sort of a lot of cover of cloud on Venus, or a lot of carbon dioxide in the Earth's atmosphere, you can end up with this so-called greenhouse effect. How does a greenhouse work? A greenhouse has glass. The light from the sun comes in through the glass, because the glass is transparent. But then, and that light heats up things in the greenhouse. But the heat, which is associated with infrared light, glass is not transparent to infrared light, so the heat gets trapped inside. So the light comes in, the energy from that light heats things up inside, but the heat can't escape through the glass, because the glass is not transparent to infrared light. And so the idea is the same thing happens in an atmosphere with carbon dioxide, that light from the sun can come in and then it can't escape. And so the temperature of the surface of the Earth goes up. Now, there are many, many, many things that can affect that. For example, one thing that affects it is, what is the average albedo of the Earth? So the albedo of something is, if you shine a light on a thing, how much of the light that you shine on it gets reflected from the thing, and how much is absorbed. So if you have something like, I think the moon, which looks to us pretty bright, is actually reflecting only some few percent of the light that falls on it. It's actually made of quite dark rock, but the light of the sun is bright enough that it looks to us like a kind of a shiny object, because enough light is being reflected. Now on the Earth, depending on exactly what the cloud cover is in the atmosphere and things like that, the albedo of the Earth can change. And if the Earth is reflecting more light, then less light is getting to the surface of the Earth, and there's less light that can cause the surface to heat up and can produce this greenhouse effect, et cetera, et cetera, et cetera. So, but in any case, the net of all this is, Well, yes, us humans have some effect. Whether that effect is big compared to the effects that are happening naturally from the change of climate is not completely clear, but we have an effect. Well, now, what consequence will that have? Well, the climate of the Earth will change. It will have changed even if we weren't around. There are things like in in Massachusetts, where I live, there's a big sort of peninsula called Cape Cod, and it's something which it's gradually being eroded away, and in time it will all be gone. And that you can see that as a consequence of, the topography of the Earth changes, the climate of the Earth changes. It's been changing for billions of years, and it's going to go on changing. And unless we put an awful lot of effort into it, we're not going to be able to stop it changing. So what? Well, that means that, for example, there will be parts of the Earth that get warmer, parts of the Earth that get colder, places where the levels of oceans go up, and so on. Well, and you might say, well, that's a disaster, but there are certainly, there are places where if you own a beachfront property somewhere and the ocean is going to go up, and the only way to prevent the city from being flooded is to put a big dike up, and that's going to hurt your view, then yes, there's a problem. If, on the other hand, you own a lot of farmland somewhere in, I don't know, Canada or something, and it's like that farmland you can't grow certain kinds of crops because it isn't warm enough to grow those, and gosh, the climate is going to change, and then you're going to be able to grow crops, then maybe you come out ahead from that. And there are parts of the Earth where there are places where it's been, that turn into desert, that turn out of desert, and so on as the climate changes. So, I think one of the things that's sort of an unfortunate feature of modern times is probably, these changes happen over hundreds of years and so on. And in the past, before people had locked down, we got a city in this particular place and so on, it's like, okay, the climate is changing, we're going to go herd our goats in a different place. And there's sort of gradual migration, and people move their yurts or whatever to somewhere else, and there's not a big deal. There's nobody says I have a property deed that says I own this piece of beachfront property and it's a problem for me, so to speak. It just sort of gradually things change. But now, because we've advanced much further and we've got a much more sort of organized society, these things are a bigger problem, and so it makes more of a difference, so to speak. And so then there's a question of are the perturbations that we humans are making in the sort of the atmosphere of the Earth, what effects do they have? Do they lead to that day when it's really hot, that day when it's really cold, that wildfire, that this, that? Well, it's really hard to know. People will try and chase that statistically. Are there more hurricanes? Are there less hurricanes? Are there more wildfires because we changed the forestry management practices? Are there more wildfires because of something to do with the carbon dioxide in the atmosphere or the temperature or whatever? It's really hard to know. And it's kind of a complicated exercise in sort of mathematics and statistics and so on. And I must say, my impression is it's just really hard to know. And so then you can ask the question, well, look, one thing we could do is just let the Earth do what it was naturally going to do, and let's just reverse out any change that we made. So we increased the carbon dioxide level, which we did, let's reverse that out. If the Earth was going to get colder or warmer at this time, let's just let it do what it would naturally do. Now, we may not like what it would naturally do, and that's a separate problem. And then we have to all agree, well, we're going to change what it naturally does. And that's a very difficult thing to agree on. But one thing we can think about is, can we reverse out what it's naturally doing? And there are a couple of different ways you can do that. One thing you do is say, well, let's, all this industrialization and all these things we're doing, let's just reverse that out. Let's go back to a time before industrialization. To me, that train has already left the station, so to speak, in the sense that, well, the world is industrialized, and the places that are, if you're in a place where you can spend a lot on dealing with power, then yes, you can have fancy, solar, wind, hydrogen, whatever, all these different forms of fuel and so on. I think there are many places where things are developing, the economy is not that well developed, and where it's like, let's just get power the cheapest way we can. And that cheapest way may not turn out to be something that doesn't sort of belch carbon dioxide into the atmosphere. I would say that another thing that I've certainly noticed when I was a kid even in England, there was a big effort to remove pollution in cities, which was very unpleasant. And that was successfully done. I don't know how much it cost. I don't know how much had to be done to factories and putting filters on factories and things like that. But that was a very immediate, very measurable, very obvious effect. I mean, I will also say that it is a little bit bizarre. I mean, is it a good thing to have clean energy? Oh, sure, it's a good thing if you can do it. When it's a trade-off between you've got terrible poverty or you've got clean energy, that's a more complicated thing. That's a complicated societal decision to make. But in terms of if you can have clean energy, why not have it? Sure, why not have it? But if it comes to having this effect, how much effort do you put in to get such and such a number of notches down on the effect that we've had on the Earth? Well, the other thing one can think about doing is just like we've had this effect because of all this industrialization, et cetera, let's just do something that counters that. Rather than rolling back the industrialization, let's just have something that balances all of this carbon dioxide that we put into the atmosphere. Let's plant more trees. There are 2 trillion trees in the world. Let's have more of them. Let's have, the plants absorb carbon dioxide. Of course, there are issues with that. There are places where people want to build cities and things rather than have a bunch of trees there, et cetera, et cetera, et cetera. But, that's an example. But then you can go much more technical because there are ways to absorb that carbon dioxide, for example, that are essentially hacks of various kinds. The one example of a couple of hacks that I'll mention. One is the plankton in the oceans, the little microorganisms in the oceans. They are guzzlers of carbon dioxide, and if you just have more of that the plankton in certain places, you can guzzle more carbon dioxide. So how do you get more plankton? Well, one way you can do it is plankton need iron. And so if you just go and dump iron into like the Southern Ocean, you can apparently, so it's claimed, you can grow more plankton. And so then they'll guzzle more carbon dioxide, you reduce the amount of, you kind of wash out the carbon dioxide from the Earth's atmosphere. There are a variety of approaches like that. There are approaches using more industrial technology where you have sort of anti-power plants where you're kind of trying to guzzle in carbon dioxide. There's an approach that uses a mineral called olivine that's very common. Apparently, olivine interacts with seawater in a way that will absorb carbon dioxide. I haven't personally verified all of these claims about these different kinds of chemical processes and so on, and biochemical processes, but there are a good collection of these processes that potentially can absorb carbon dioxide. There are also things you can do, like you can change the albedo of the Earth. You can put things in the Earth's in the upper atmosphere that cause less sunlight to reach the surface of the Earth and cool it down. You could even put giant, pieces of mylar up into space that reflect light from the sun. Okay, but the thing that usually happens when you start talking about these things is people say, but who's going to decide to do that? Somewhere there's going to be this great big, you look up in the sky and there's going to be this great big black thing there, and that's blocking sunlight. Is that really what we want to do? And then what tends to happen is with geoengineering, which is this kind of term for this area of kind of change the planet by using these various kinds of hacks. The thing that you have to do when you start thinking about these kinds of hacks is you have to say, can we really predict what's going to happen if we start, putting things pouring iron into the Southern Ocean, and producing plankton? What's going to happen? What's really going to happen? And of course, then you have to be able to run climate models, and you have to trust the answers. And one of the things that's sort of paradoxical is that people are on the one hand saying, look, our climate models say the Earth's going to heat and warm by this amount, the sea level is going to go up by this amount, et cetera, et cetera, et cetera. And they say, so we got to do all these things. And they say, okay, great, let's do these things. Let's do this piece of geoengineering. Let's feed that into these models. After all, we think we can make models. let's put in this geoengineering sort of intervention and see what happens. Usually what you find is people say, well, let's not do that. We're not really sure these models work that well. Gosh, something else might go wrong. So it's a bit of a paradoxical situation. And of course, it's deeply steeped in politics, because the details of, which country pays this amount for carbon and does this, and, what constraints are put on different kinds of activities in different places. Those are questions of society and politics and things. They don't have much to do with science. And, this is not really the subject for today, but maybe it's more of a history question. The whole dynamic of the intermeshing of sort of politics and science in the climate situation has been, for me, as just I would say a science-oriented person, it's been kind of horrifying to watch, because in a sense, whatever the science may be, it doesn't really matter anymore, because there's enough kind of societal will to go in a certain direction that's what people think they want to do, and that's what society wants to do. And I don't think it's horrible, but and I think it will lead to some good science and good technology. And personally, I think it's probably a good thing not to burn those squash trees from the Carboniferous period that we're using as oil and so on. But where there was only one time in the history of the Earth that stuff got made. But I remember, it's terrible how these things work, because I remember there was a time when people said oil is going to run out. We're just going to run out of oil. There's not going to be enough oil left. And so oil companies have geologists, and I know some of them. And so I was asking questions about, is that really true? And obviously, if you're an oil company, you go prospecting for, you go trying to figure out, where is there oil? Should we buy the rights to be able to drill in this part of the ocean or in this piece of land, because, gosh, we might find oil here. And so it's a big deal to predict, what geological formation will have caused there to be oil formed in a particular place. And, so when you ask the question, what are the places where there might be oil? The answer is, it's really hard to know. And basically, people will say, how much are you prepared to spend? Because if you're prepared to drill deeper, do more investigation, etc., you can find more oil. And then obviously with fracking, that was another hole, and shale and all these kinds of things. There were places to find oil where we didn't think there was oil before. And it's really just a question of how much are you prepared to spend to get that oil. It's not the case that we're going to run out of oil. That's far away, or at least nobody knows how far away that is, because nobody really knows what the ultimate oil deposits on the Earth are. It's really just a question of, how can we retrieve them, and what interesting technological ideas are there to get them. I mean, one of the issues is an oil reservoir in the ground is, it's in porous rock, and there's just a whole bunch of oil there, and there's also water there. And you drill down, and you have to, the question is, can you get the oil out of the ground? And can you, for example, pump down high pressure water to push oil out? And how does that work in porous rock? That's an interesting subject. I can talk about porous rock at some point, and how some of that works. In my youth, I happened to do a piece of consulting for an oil instrumentation company that I think perhaps was useful in some of the modeling for how that all works back in the 1980s. Well, anyway, so that was, let's see, what did I not mention in the world of, in a perfect world, we'd have perfect climate models, and we'd know exactly what was going to happen, and we'd know if you turn that geoengineering knob, this is what will happen. And then we can have a great big debate. If you could turn the average temperature of the surface of the Earth up by 1 degree, some people would say that would be fantastic, and other people would say that would be horrible. And unfortunately, things like the carbon dioxide level, that's a more or less, not quite, but more or less, it's a global thing for the atmosphere of the Earth. And so we're kind of all in it together, so to speak. And you can't just sort of say, well, in my country, we're going to do this, I don't really care what anybody else does, because it's kind of, we're all on this planet together, so to speak. And so it becomes a very complicated sort of societal, political set of decisions. What do you actually want to have happen? And one realizes, even at the level of much more local things, which we still don't know how to do, but if we knew how to do cloud seeding and we could make it rain or not rain on a particular day reliably, you'd have a whole discussion within a city, for example. Do we want it to rain today or not? How do we decide whether it should rain on Monday? Do we take a vote? How do we, what happens to the minority? Does the minority get to choose for some number of days in the year? How would that possibly work? In a sense, we're better off just leaving it to nature, where nature will do what nature does. But then it's a little bit of a difficult sort of logical question. If we are putting our finger on the scale, so to speak, to change a little bit what's happening, but we don't really know what's going to happen. Nature is going to do something which we don't know. If we change nature, it's going to do something we don't know. What do we do about that? It's a difficult thing to answer. But as I say, it's one where a lot of the kind of decision making is something that's gone into the political realm rather than the scientific realm. And I think personally that the technology of clean energy and so on is a fine thing. And whatever. Okay, let's see. The questions about carbon capture and whether this is yeah, it's a good question. Whether if you capture the carbon, I'm reminded, I found recently a strange essay that I wrote when I was like 11 years old, which is 1971. So when the world was a different kind of place, but where one of the problems was the sort of buildup of trash in the world. And so in my 11-year-old essay, my conclusion was the ultimate thing to do with trash in the world is put it on a spacecraft and throw it into the sun. So I don't know what, I think there are the question of how sort of carbon is ingested inside the earth and what happens in different kinds of rocks and carbon in rocks versus carbon in the atmosphere. I don't know how that all works. I will say that the total amount of carbon in the atmosphere is pretty tiny compared to the amount of carbon in rocks, because rocks are solid and they have a much higher density of atoms. And so it's inevitable that there's just going to be a lot more carbon there than there is ever in the gaseous atmosphere. Okay, so Motu was mentioning, is climate change necessarily bad? As in, what equilibrium may we reach after the instability is stabilized, and what would that equilibrium necessarily be worse than the one we have? The other question is anything destabilizing? That's not clear either. I mean, in other words, if it is the case that we have made changes that have a significant effect on climate, which probably we have, who knows, are they destabilizing changes, or are they changes that just make some parameter move at a different rate? And there's nothing, it's not going to increase the volatility of climate change or anything. It's just going to mean that, the time when the next ice age happens, let's imagine the next ice age is 50,000 years away. Maybe we just moved it to 70,000 years away. I don't know, is that good? Is that bad? Who's to know? I don't think there's any real evidence that sort of unpredictability of the climate has increased. I think that there may be a perception that it has, because weather forecasting is hard, but we expect everything to be forecastable, but it isn't. And there are sort of fundamental sort of scientific reasons why these things are hard to predict. That's a different topic, about particularly the phenomenon of computational irreducibility. In the case of weather forecasting, a famous thing is sort of the chaos theory effect. In fact, back in 1963, a chap called Ed Lorenz, who I used to know, meteorologist at MIT, figured out that in a kind of very simplified mathematical model of the weather, if you just changed one number by just a tiny, tiny bit, you change one number in its 10th decimal digit, then eventually that change in the number in the 10th decimal digit could affect the overall behavior of the system. So that sort of turned into this idea that, if a butterfly flaps its wings at a particular moment, that could lead to a hurricane, which wouldn't have happened if the butterfly hadn't flapped its wings. Well, the truth of that situation is those times when the butterfly flap really makes a difference are a very, very, very tiny set of times. Most of the time, the effect of the butterfly just dies out. Most of the time, it's like you flap your hands in the air. Most of the time, the air currents that you produce will be damped out by viscosity, essentially friction in the air, and no consequence. But just sometimes, the time when you flap your hands will cause that little packet of air that was, where something was just on the edge of some air being pulled up from an ocean somewhere that to produce a hurricane. It was just on the edge of, would it make a hurricane, would it not? At this bifurcation point where it's going to kind of go one way or the other. It's like you have a beam and you're pushing on the two ends and it's going to buckle, and it's either going to buckle up or it's going to buckle down. And it's kind of a very detailed question whether it goes up or whether it goes down. And so there can be these situations where you're at these sort of bifurcation points where it can be sensitively dependent on these initial conditions. And in the case of the weather, there are these places where that will happen. In general, well, it's a little bit more complicated. And when you do weather forecasting and you make changes in the initial parameters, there is a progressive deviation of the final result from the initial result. But there are questions about how fast that happens and so on. There are questions about what can make a change, what doesn't make a change, and so on. So the real reason for difficulty, I think, in particularly long-term climate forecasting is the story of computational irreducibility. It's a story of there are computations where the only way to work out the outcome of the computations is to just do the computation. And that's, but unfortunately, you both have to do the computation and you have to get all the details right in order to correctly predict that climate kind of thing. So it's a really challenging thing. And I think it's, I haven't personally I have looked at some weather forecasting codes. I have not personally looked at the climate computation codes, the programs. I think they are fairly, it's very difficult to know what the right answer is. It's very difficult to know whether you've got all the right effects in there or not. I mean, I'll give you two other examples, perhaps, about complicated codes where all kinds of strange things happened historically. When people try to work out the explosion of stars and supernovas, that's a complicated problem of nuclear physics. And people had these big codes to try and work it out. Those codes happen to be very closely related to the codes that were used to work out nuclear weapons explosions, because those are also a story of nuclear physics and nuclear reactions. Well, there was a long period of time when people said supernovas just can't happen. Well, it turned out there was a detailed mistake of particular neutrino opacity data cards, I think, that have been mistyped that caused the calculation to just get the wrong answer. And that's a feature of these complicated codes that depend on many things, depend on the details of how many cloud layers and how many mountains you put in, and whether you account for some effect of ice crystal formation or not, and all this kind of thing. What matters, what doesn't. Really hard to know. And it's really hard to debug these codes because it's not like you say, well, let's just rerun it and let's just see whether it reproduces correctly what happens on the Earth in this case, in that case. It's very hard to do that kind of testing because we only have one Earth to look at, and we only have one chain of history with all of its details to look at. Another case where people were concerned with these codes was in nuclear reactor safety, where again, it was really hard to know whether the calculations would actually come out correctly, and sort of it's always a challenging thing. All right, I think that's about all I can say. About yeah, various people are commenting here on, do we really understand the plankton well enough? Or will they make something else worse? So who knows? I mean, that's the problem. you kind of have to know everything. I mean, we've kind of seen the effect of it's hard to know what's going to happen in the pandemic and the epidemiology of this pandemic, where people are also saying, we can calculate, we'll figure out, using simple models of epidemiology, we'll figure out what's going to happen. Well, it turns out it was more complicated than that. It was really hard to figure out what happens, and whether we've even accounted for all the correct effects is very unclear. Whether we've accounted for the correct effects of human immunology, of kind of the people with long-term carrying of low levels of virus, all this kind of thing, we don't know. The one thing that has happened in this pandemic is amazing focus on virology, the study of viruses, and no doubt more will be learnt, or more has been learnt about that in just these this year and the next few years probably, than has been learned throughout the whole history of the subject before that, because endlessly more testing, more experiments, more theoretical analysis has been done. But it's very notable that we've been very unable to predict, and I knew this back from the beginning of this pandemic. My son Christopher did a particularly big study of this, looking at kind of the effects of different kinds of ways that people could be connected to each other. The very standard model of epidemiology, so-called SIR models, make the assumption that all humans mix. So, you're meeting strangers all the time. Everybody, if there's a certain fraction of people who are infected, they're going to infect some other people, and everybody's just randomly mixed. But the truth of it is, in most parts of society and so on, people aren't meeting strangers all the time every day. Some places they are, but in many people are not. Many people have some kind of definite network of people that they interact with. And as soon as you start dealing with those definite networks, you have completely different results from what you get with these sort of random mixing models. And people try and partition the random mixing models and say, let's have a 10-compartment random mixing model where people of this age range won't mix with people of this age range, whatever else. But in the end, it's very hard to know. And the question is, are the results you get robust, independent of what you assume about how that mixing works? And the answer is no, they're not. Only a very few results are robust and come out the same independent of how that mixing works. Many results come out completely differently. Like an example of a result that seemed to be pretty much independent of that is, it's worse for contagion to have a small number of large gatherings than a large number of small gatherings of people. That almost independent of how the network of connectivity of people works, that works that way. But lots of other things you can't tell. And this is a great example of sort of computational irreducibility at work, and also the fact that you have to know what effects do you really need to account for in the model and what don't you to make a correct prediction. And it's turned out to be really difficult in this case. Okay, Parmenides is commenting, think how lucky human beings are. We had one asteroid hit the Earth to make the moon, gives us seasons, plants to grow and make oil and coal. Then an asteroid kills the dinosaurs that might have eaten us. Then we get enough free reign to start up nuclear fission, nuclear fusion, and so on, become self-sustaining, etc. What luck we've had. I have to say, one of the things I've noticed from studying biology and natural selection and so on is that one thing that biology is always doing is being opportunistic. When a mollusk randomly picks some shell of a certain shape, then it discovers that, given the shell of that shape, I can do this cool thing and that other cool thing. I doubt that, so in other words, there is a lot of luck to be found, so to speak. That is, if it turned out we didn't have a moon for the Earth, and we had a different characteristics for our seasons and whatever else, then, I think sort of, if there had been life formed on Earth, it would have found a way. It will be different from what we have now. Let's say the ozone layer didn't exist on the Earth. Well, does that mean there couldn't be any life because it would all get burnt to a crisp? No, absolutely not. There are forms of life that are robust against ultraviolet radiation. And, we would have been different from the way we are. We are the way we are, because we fit into the kind of niches that exist on the Earth as it is. But I I think it's fair to say that there's tremendous kind of opportunity for life to be a different way, so to speak, even within the detailed biochemistry that we have. I think there was one other comment here about hydrogen fusion. Yeah, well, people thought after the first nuclear weapons and so on, the first hydrogen bombs, that it would be easy to make energy the same way the sun does by nuclear fusion of hydrogen, for example. It turned out to be really hard to contain. You have to get these plasmas up to 10 million degrees centigrade and things. It's really hard to keep something bottled up at that temperature and so on. And people have been trying for 70 years now to do that. For various reasons, there is a recent great enthusiasm for being able to do controlled nuclear fusion. And there are a whole bunch of companies that have started up with various different designs for how to use magnetic bottles and things to kind of box in this very high temperature plasma, and maybe in the next some number of years, controlled nuclear fission will be achieved. It's easy to achieve in very small amounts, but it's not possible to achieve it at the level where you're getting out more energy than you're putting in. Let's see. I think I've been going a while here, so maybe a few more questions. There's a question here: do we think there are life forms out there where the spectrum of visible light is totally different from ours? What you count as a life form is a complicated issue. If you say things that have chemistry similar to ours, which may be a very small chance, but let's say that they do, then absolutely the range of frequencies of light that we are sensitive to is just the ones that happen to make it to the surface of the Earth, pretty much. And that's what the photoreceptors in our eyes, it all started with the trilobites. They were the first critters that had eyes back in the Cambrian period. Their photoreceptors, a protein was developed that or arose that had sensitivity to photons of light in this range of frequencies. And, it worked for the trilobites, and we've been going with it ever since. I don't actually know if the trilobites had the same photoreceptors that we do, but I bet that I think it's very likely that they did. It's sort of very embarrassing. If you look at many of our biological mechanisms, molecular biology of us, there are so many molecules that have been very conserved for the last billion years or more in the history of life. It's like we have the same mechanism for dealing with, I don't know, even things like insulin and so on that existed in these organisms just like a gazillion years ago. It's like we didn't invent a lot of new stuff. Whatever it is that we humans got to get working was a very thin thing on top of all of these layers of biology that were already existed. All right. Let's see. Question here from Guile. Do you think there's a plateau we must break through for space exploration to be more feasible, or is our progress as is good enough? Look, when I was a kid, everybody knew there were going to be Mars colonies by the 1990s. Obviously, there weren't. Something went wrong. What mainly went wrong was not that it was impossible, but that people said, what's the point? Why are we going to spend billions of dollars sending spacecraft to wherever? We've got plenty of problems here on Earth. Let's go work on those and not sort of burn our money up in rocket fuel, so to speak. And there are applications of space, communication satellites, reconnaissance things like that have gradually, the GPS system, things like that have gradually become more significant, but they don't really justify going to the moon yet. They don't really justify going to Mars. And we don't really quite yet know what the big payoff for having a lunar colony, for example, will be. I don't know what it will be. It's an interesting question. It's sort of an interesting thing to think about. Just like when computers were first invented, what will be the big payoff from that idea? It wasn't sort of the solving of mathematical problems, although we tried to do our part for that. That was sort of an original idea for things about computers. It was all kinds of other things about storing information, communicating, et cetera, that turned out to be the biggest obvious wins for computers. One of the more bizarre, you don't know what's going to happen type things, this phenomenon of computational irreducibility that I mentioned, that I kind of figured out in the early 1980s, this way of understanding that there are computations where you kind of need to go through all the steps in the computation to get to the result. You're kind of burning computational effort to get to the result. And sort of a question of what's that going to be useful for? And in a just a very bizarre turn of fate, that's, I think, what turned into the kind of proof of work idea for cryptocurrencies, for things like Bitcoin, that you kind of show that you have a valuable thing by burning computer time to do that. And you have to burn the computer time because of computational irreducibility. And so I certainly would never have expected, when I was inventing that sort of abstract idea of computational irreducibility, that it would turn into this thing where you're proving you did computation and you're burning electricity to do it for the sake of producing cryptocurrencies. Just never would have occurred to me. So similarly, when we talk about putting a colony on the moon, it's just not obvious what that's going to be good for. I mean, yes, we can put, we maybe can make a great radio telescope on the far side of the moon, and maybe when we make the great radio telescope, we'll discover that we can be part of a giant galactic conversation with all those aliens and so on, and that will tell us all kinds of new discoveries. Or maybe it will turn out that the moon, I don't know what the applications of having something, having colony on the moon will be. Maybe there'll be a sort of a giant trend of running giant ads on the surface of the moon, and what good that will be, I'm not sure. I think it'd probably be a kind of a weird thing. But I think the question of sort of, is there a technological plateau that needs to be got past? I mean, I think one of them is reusable rockets, and that seems to be being that problem is being licked right now. That problem is being solved. I mean, that's been a difficult problem to solve, but that one looks like it's happening. I mean, another one is reliability. It traditionally has been the case that like 1 in 50 rockets blows up. I don't know if that's still true. Clearly, having more sensors and more ability to figure out what's happening earlier, maybe more ability to simulate things, can change those numbers. That's obviously an issue. And no doubt there are ways of building, an increasing number of sort of fail-safe, safety layers that can help that. But, is there some sort of magic idea that will allow the cost of sending things into space to go down? Obviously, reusability is a big feature of that. But there are other things, like there are ideas like, rail guns, where you'll use some electrical mechanism to kind of shoot things at very high speed and maybe shoot them into orbit. There's also these things where there's the scheme where you're spinning things around very, very quickly, and suddenly you kind of let go and you open this door in the system, and you let go, and this thing will spin off into, it's been spinning around, will be the centrifugal force, so to speak, will make the thing just zoom off into at a high enough speed to go into orbit. Some of those kinds of schemes have issues because they're very high accelerations, and certainly humans aren't going to survive through all of that, although probably electronics, for example, can survive through that. So there are things like that will reduce the cost of reduce the cost of putting things in space. And then there's a question, what are we going to get for putting things in space? If there's a point at which it's cheap enough to put things in space, will there be dramatic new uses for space that haven't even become conceivable yet? I mean, this certainly happened with computers. Back when computers, even when I started using computers in the early 1970s, there were tons of things that you would never have considered using a computer for, because computers were way too expensive to do any of those kinds of things with them. And yet, by the time computers get cheap enough, there is these dramatic uses that make high value for computers that happen because they suddenly got cheap enough. and the same thing could happen. It could happen with things like exploring the moon. There's a comment here. There's a comment here from Neuro about sustainable energy, going back to our discussion about climate change, mentioning they're skeptical that renewables like solar and wind can meet growing demand. Can nuclear approaches work better? I don't know. I haven't really studied the solar and wind case. I mean, I think there are the conversion of light into electricity by photovoltaic cells. The big issue there is how efficient can that be? And then there are more minor issues like how much does it cost to actually put out that number of photovoltaics? So in parts of the world where you're in a giant desert where there's tons of sunlight, what happens when you get a whole layer of sand and you have to have these little critters that come and clean the sand off your solar panels? And then, of course, there's the question, if we put enough solar panels that are absorbing enough light from the sun, how does that affect kind of global climate, even by itself? It's like building, I don't think that the area of the solar panels is large enough that it's going to have a big effect, but it's not clear because it's like cities have an effect because they're much darker than the surrounding area. And solar panels are effectively like that too. But people have been looking for a while for kind of a magic new substance that can be a more efficient converter of the energy of light into electricity. None has been found yet, but that's something that could be found any day. Somebody could find some strange chemical compound that would be just a spectacular photovoltaic with much higher efficiency and very cheap to produce, and that would change the whole equation for solar power. When it comes to wind, these big wind turbines, they're really expensive. And it's a complicated issue what the effect, having a bunch of wind turbines at different places, probably doesn't, locally it has an effect on the wind. It probably doesn't have a global effect. We're probably far, far away from having a global effect. What is the sort of the price curve of how much does it cost to build the wind turbine versus how much are you getting for what it costs? Part of that is a societal decision. If you say, we just don't want to be burning coal anymore, so let's spend the money on lots of wind farms. Well, that's a decision one can make. It may be an expensive decision, and that's a complicated question of economics, and let's not segue into talking about economics here today. So Alistair observes about talking about going to visit, put colonies on the moon and so on. Makes the perhaps tongue-in-cheek comment, we could study moon rocks in greater detail, and then after that we can do it again. Yeah, well, the geology of the moon is kind of interesting because unlike the Earth, which has an atmosphere and where there's been erosion and water, there's been rain and that washes rocks away, and there are oceans and that kind of carves things out, and there's been and there's soil and there's all kinds of things happening. There's gradual erosion of rocks on the surface of the Earth. On the moon, what was there 4 billion years ago is probably still there today. And the moon doesn't even have a liquid core. There are no volcanoes. It's just the way it was when it started out, 4.6 billion years ago or something. And it's I think the case that a footprint there that in the little lunar dust, it's still going to be there 1 billion years from now if some tourist hasn't erased it. Nothing much happens on the moon. It's a very pristine environment in which to explore what the early solar system was like. Why do we care? Well, it's interesting. I had a friend, who had a company that was, I guess they're still going to send a moon probe, although it's been multiple times delayed. But they had the idea of bringing back moon rocks. And then the big idea was, gosh, diamonds are valuable and people think diamonds are cool. What about moon rocks? All the better to have, a moon rock ring than a diamond ring. It's something more exotic, more rare, and so on. I kept on trying to persuade this person I know, get some crystallographers involved, figure out how you can, find the right kind of moon rock and cut it the right way. Because, with diamond, when people have diamonds that they put in rings and so on, that they wear or whatever, part of the trick of diamonds is that their faces, they're cut in a particular shape so that when light goes into the diamond, the refractive index of diamond, which tells you the speed that light goes at inside the diamond has a refractive index of 2.7. So light goes 2.7 times slower in diamond than it does in the air. And that causes there to be a lot of total internal reflection inside the diamond. So the light kind of goes into the diamond, it bounces around a bunch of times before it comes out. But the details of how it comes in and how it goes out depend on all the angles of all the cuts in the crystal. And so depending on the detailed crystalline structure of diamond, you make these cuts at different angles and so on. And you have to figure out the same kind of thing for moon rock, or if there even is a moon rock that can produce the same kind of interesting visual effects that diamonds can produce. So that's sort of a feature of studying moon rock. I think that we don't really know quite what the details of what might be mineable on the moon that will be useful. I mean, it looks like different on the Earth. It's kind of a weird thing where you say, where are the gold deposits on the Earth? Well, there are particular countries that have lots of gold deposits. Where are the uranium deposits? Where are the tantalum deposits? Where are the niobium deposits? The one thing that's a general rule is if it's a big country, there's probably deposits of stuff somewhere in it. And, that's been significant in sort of in mining around the world. The big countries will have some gold deposit, some tantalum deposit, with some probability somewhere. But in the formation of the Earth, for whatever reason, the tantalum all wound up in different places. I think there's, Rwanda, China, various other places have tantalum. Who knows why? But just as there's segregation in these different materials on the surface of the Earth, so also in the solar system, there's segregation of these things. So different asteroids, for example, one will have a large amount of one particular element, another will have a large amount of another particular element. On the moon, I don't think we know a good kind of geological survey of the whole moon of what exists there. I mean, maybe there's lots of gold somewhere on the moon, for what that's worth. Maybe that'll be discovered right around the time when the actual value of gold is no longer important and it's all cryptocurrencies all the way down. I don't know. So it's a very interesting question. What, if we had a moon colony, what would it be good for? And as I say, I think there's a good chance that it would turn out, well, we can ask the same thing about the Antarctic, for example. When there are scientific research stations in the Antarctic, what have they been good for? Turns out there are some cool things you can do there, quite literally in terms of temperature, but also things like there are particle detectors that have been built at the South Pole. There are observations about the atmosphere that can be made in Antarctica. There are things like that. It's not dramatic. It's not like, a city of 100,000 has grown up in Antarctica because there's so many important things to do there. But there's some things. And whether it will turn out that on the moon, there's sort of Antarctic level things to do, or whether there's more or whether there's less, I'm not sure. Interesting question, interesting thing to kind of think about. All right, well, there were lots of other interesting questions here about very different topics, but I should wrap up for now here. Thanks for joining, and see you another time.